This lecture is on a new data structure that we are going to study. This data structure is known as trees. I've already given you a brief introduction in one of the lectures before. So trees, as the name suggests, when you imagine a tree, you have a root and it grows upwards. But in data structures, we look at the tree upside down. So at the top we have the root and then we have the branches. So there are many branches that can come out of the root. Okay, and then from the branches you can have further branches. So when you look at it upside down, you have a root and then you have multiple branches coming out. So like your earlier data structures, this data structure is non-linear. Non-linear means in linked list you had a start pointer and then you had links to next nodes, and you would traverse the node in one direction and you only had one place to go. In case of doubly linked list, you went from one node to another. You had a double pointer, in the sense you had a front pointer and you had a back pointer, but even then you were going only either in the forward direction or in the reverse direction. So if you would just see what path you can take in both singly linked list or doubly linked list, or for that matter stacks and queues, it is a linear path. So you go forward or you go backward in one direction. But when you think of a tree, you have the root and then you have branches, so you can either go to one branch or to the other branch. So you have multiple directions where you can go to, and based on that you will reach different locations. So this data structure is important uh, in terms of its applications in a multitude of applications. A simple tree-like data structure that you can imagine is like your uh, organization hierarchy, where you have, let's say, for example, in our college we have the director, then you have the HODs, then you have coordinators, and so on. So we move down each level. So that would be an example of a tree, as in where you can imagine where you draw a tree or a family tree. You have grandparents, then you have their children, and then their children, grandchildren, so on, and you draw a tree-like structure. So you have a pair of parents from maybe from where you start, which is basically from where you want to trace your family, and it grows all the way down. It doesn't grow up. So our trees grows in the downward direction and not in the upward direction. So it is non-linear, just like your graphs. Graphs you're going to study afterwards, after we finish trees, and we have to go through sorting procedures after this. So they are flexible. We'll see how flexible they are and where we'll use them and what are their applications as we proceed in this lecture. So again, you have nodes or data items which you store in the tree. So the tree has nodes, and each node contains a data item. It can have one data item or multiple data items. For simplicity, what we do is we usually take one int element in the node and pointers at whatever number is required. So like I said, the tree originates from the root, so it is a special data item, specifically from where your data structure actually starts or originates. And then you have branches. So the items in the branches, you can have one, two, or not one, two or three or more branches based on the structure of the tree. So obviously there'll be many types of trees, which you will see in a while. So whatever items are in the trees, or whatever items go in each branch, they are disjoint subsets. So our items will find their locations in the tree based on a particular property of the tree. Okay. So these subsets or disjoint subsets, they are in itself trees. So you can think of tree as a root and two subtrees or three subtrees. So each subtree will have its own root and its subtrees further down. We'll just see in a picture in a while. So we have a root, and if there are only two branches in the tree, we'll have a left subtree and we'll have a right subtree. Okay, If you have more than two subtrees, then accordingly we'll define our tree like that. So this is your tree. You have a root growing downwards. This is our root, and then you have a left subtree. I have marked it with orange here, and you have a right subtree. So each subtree in itself is a tree. So you can think of it as having a recursive structure. So the tree comprises of a left subtree, a right subtree, and a root. Okay, so here each root here has its own left subtree and right subtree. So right now we have just created nodes for the left subtree. It can grow downwards depending on the number of items in your tree. So the tree definition is recursive. So whenever we write tree functions, we usually use the recursive procedures, because whatever we want to do with the tree, if let's say you want to search something in the tree, so if that element is not in the root, so that element is either in the right subtree or in the left subtree. So you can call that search function on the right subtree or on the left subtree and see where you find that item. We'll see more of that later. So when we talk about trees, there are few terms that we use in describing the trees. So the first thing is that every tree has a root, so that is your basically starting point. So in this case, our A is the root. So root is basically a node. So this tree contains nodes just like a linked list contain nodes, and those nodes are linked by way of pointers. So here also we have nodes and they are linked by way of pointers. These lines, they represent the pointers, and these pointers, they can be multiple pointers originating from one node. So a tree is a set of or a collection of nodes. The organization of these nodes, the structure, is what is in the form of a tree. So you have nodes and you have links. So this is a link. So it's basically a pointer. A points to B. A also points to C, and A also points to G. So we say if the A is the root, B, C, and G, they are the children of A. Okay. So the children of A are B, C, and G. The children of B are D and E. Okay. And if B, C, and G, all three in this row, if all of them are the children of A, that means they are siblings. Okay, so that's the term they use. So let's first go in order. Degree of a node. If you see, degree of a node is the number of subtrees that are originate from that node. So if you see A in this particular figure, there's no specified order as to what is the degree of each node. So based on the degree of each node, your tree will be defined as what kind of a tree it is. For now, this is just an example tree. So the degree of A is 3 because it has 3 children. The degree of B is 2. It has 2 children. Degree of C is 1 and degree of G is 2. If you see all the nodes, D, E, F, H, I, they are the last nodes of the tree, basically the terminal nodes of the tree. They don't have any children, so their degree is 0. And since their degree is 0, they are also known as the leaf nodes. So basically when you have a tree, it grows, and leaf is kind of the end point of the path that you follow from root to the branch to the leaf. Okay. So like I said, terminal node, your nodes D, E, F, H, I, they are terminal nodes or leaf nodes. Terminal in the sense your tree terminates there. Then you have non-terminal nodes. There are two terms I have written here. Non-terminal node would be any node except the root node whose degree is not 0. So non-terminal, obviously, which does not end. If the degree is not 0, it is a non-terminal node. Okay, except the root. But you have another term which is called internal node. So any non-leaf node is an internal node. So for non-terminal, they exclude root, and for internal node is any node other than the leaf node, a non-leaf node. Okay. Then, like I said, siblings, the children of a node are all siblings to each other, and like B, C, and G are children of A. So A is their parent, and B, C, G are the children of A, and B, C, G are siblings. Okay. Now, if you see, the parent is, let me just erase this. A is the parent, it is at one level. It is connected with B, C, and G through separate links, and they are at one, you can say 1 degree away, or they are one step away from C. So if you have to go from A to C, you have to basically traverse one pointer. For example, in case of a linked list, when we go from one node to another, you go one step further. If you have to go to the second node, you will take two steps. So to reach to B, C, and G from A, we will take only one step. So if this is, we say if this is at level 0, B, C, and G are all at level 1. And to go from A to D, you have to take two steps. First, you go from A to B and then B to D. Or if you have to go from A to E, you take two steps, A to B and B to E. So the level at which D and E are present, it is level 2. So this is level is also known as the depth of the tree. You'll see in a while. So root node is always at level 0. So children of root are at level 1. The grandchildren of root will be at level 2. So let's say if the level is for any node is n, its children will be at level n plus 1. Grandchildren will be at level n plus 2. Then you have edge. If you have studied graphs in any previous course, in graphs we have nodes and they are connected with edges. Okay, so similarly in trees, the nodes, whether it be parent and children, they are connected via edges. So the line basically connecting two nodes, it is an edge. What is it in terms of the data structure? It is actually a pointer going from one node to the other node. It's not, the pointer doesn't actually go, but the node A will tell you the address of node B. That is the child of A. Path, the sequence of consecutive edges. For example, if you have to go from A to E, you have to take the path A to B and B to E. Okay, so this A to B edge and the B to E edge together comprise the path from A to E. Then depth or height of a tree. It's actually depth and height of a tree. So the maximum level of any node in a given tree is the depth of or the height of the tree. So how high is the tree? It is how many levels it has basically. So what is the maximum level? You have 2. So depth or height of the tree is 2. Then, okay, there's another term they use. They call it the forest. Forest is basically a collection of trees. That is the general definition of a forest. What is a forest? When we think of a forest, we think of a collection of trees. So if I remove A from this tree that I have here, that means all these three edges are gone. Okay, let me just first remove this. So if I basically remove A, so there'll be no more path here. So what I'll be left with is this here. So I have this subtree B, D, E, C, F, and G, H, E, and A. So I just remove, basically I take out A and put it separately. So A is not linked to B, C, and G now. So I get 3 different trees. Okay, these are all trees. This node A itself is a tree. Okay, but just one node in the tree. So this collection of trees is known as a forest. Okay, now you have many types of trees which have been defined in data structures. The most basic ones are binary trees that have only two children. Okay, so we'll be doing binary trees in details. Then you have other types of trees which are known as avial trees. You have red black trees, you have bee trees, and many other types. which have specific features and functionalities which are applicable at many places. So for now, we cover binary search trees in detail. Uh, then, in case we get time at the end of the course, we'll do a bit about ABL trees and maybe B trees a little bit. Okay. So depending on the structure of the tree, like I said, a tree can have a node, and this you can have multiple branches going out from the node or the root node. In a binary tree, for example, we restrict the number of children that any node can have to a maximum of two. Okay, so if there are two children, you will have a root, you will have a left subtree, and you will have a right subtree. So this is the structure of the tree, and this will be followed at every level. Every subtree will have the same property. Okay, in case of this example, A had three children, so the degree is 3. Okay, so depending upon the type, degree, and the kind of structure allowed, trees can be classified into various types. Okay, how we place the data inside the tree is also a feature which will define what kind of a tree we are using. We'll just see in a while. So first of all, we'll focus on binary trees. So a binary tree is a tree, again a hierarchical data structure in which each node has at most. So when I say at most, it can have either no children or one child or two children. Okay, so there'll be a left subtree, the root, and the right subtree. So these are many these are some kind of features of the tree. They help you in efficient insertions and deletions, and they are flexible in the sense that when you have a tree and you have subtrees, uh, with only one pointer change, we can move an entire subtree from one place to another, which is a very good feature. If you remember, why we moved from arrays to linked list was because in arrays you had to when you had to insert somewhere in between, you had to shift all the elements, and in case of linked list we could do that insertion with a couple of pointer changes. So similarly here, they are so flexible that you can move an entire subtree which can have any number of nodes inside. With one pointer change, you can move it entirely somewhere else. Okay, and that you can also insert efficiently. We'll see when we do the actual trees, and they are efficient in searching. We have binary search tree for that, and they are basically, why do we have trees? The concept arose from the fact that you can actually represent a structural relationship which was in the form of a hierarchy, like a family tree or a organization hierarchy. You can actually represent it using a data structure. Okay, now binary trees, the condition was a node can have at the most two children, but then it can have either 0 or 1 or 2. So the flexibility that is allowed in terms of how many children it can have, should it always have two children, should it have 0 or 1, and so on, based on that we define different types of binary trees. A full binary tree, every node has either 0 or 2 children. So when you have children in a node, you either have 0 children, which means that you are a terminal node or you are a leaf node, or you have two children. You cannot have just one child. Okay, so that is a if that is the case, it is not a full binary tree. So either 0 children or 2 children. Then a perfect binary tree, if you see here, this is a full binary tree. This node has no children. It is a leaf node, but it's at a different level. So here in a perfect binary tree, the leaf nodes will all be at the same level or same depth, although the degree is still 0 and 2, which is the same in case of full binary tree, but you have that extra restriction that all the leaf nodes should be at the same depth or level. So you cannot have a degree 0 somewhere in between the levels. Okay, now this is your perfect binary tree. Now there's something known as a complete binary tree. So in a way, complete binary tree is a tree which is trying to become a perfect binary tree, and but in that procedure it can have its last level incomplete. So basically, you are allowed to have the last level partially incomplete. So whenever you are adding elements to this kind of a tree, you add, let's say, root, then you add the left node and the right node. So first level is complete. Then you add this 1, 2, 3, 4. Second level is complete. You are adding in the third level from left to right 1, 2, 3, and next you'll place here. Okay, so the nodes that you're adding, you're putting them as left as possible. You cannot add a node here next and have this empty and this empty and this empty. Okay, so you cannot have that in case of a complete binary tree. It is a binary tree in which every level is filled except for the last level, which is where you are actually adding next. Now there's another concept of a tree. So before I, okay, I wanted to show you something. I don't know. Okay, it's not here. It's some other notes. Now, for example, if you create a binary tree like this, let's say, so every node has only the right child. There is no left child. No node has a left child. So if you look at it, it is a linear list. You are moving only in one direction. So it kind of becomes like a linked list. You start from the root and you go right, 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 right all the time. So you have a tree that is basically converted into a linked list now. Okay. So, and it is not balanced in the sense, ideally, when we draw a tree structure, we would want it to be a balanced structure. Balance means you should not only be adding nodes, let's say, only to the left subtree. You should be adding it equally. So to keep the tree balanced, one side should not grow enormously large and the other side is very small, which defeats the purpose of actually creating a data structure trees and doing these complicated manipulations with the tree and not getting efficient results. We'll see when we do actual examples. You'll see what I mean by this, that we actually lose the very, you can say, the essence, or we lose the properties which efficiency of trees if we let them grow only in one direction. It basically does not serve the purpose of actually constructing a tree. We are constructing a tree to make some things efficient, and if you do not get a proper tree structure at the end of it, it kind of creates imbalance and you don't get the desired efficiency in terms of time and space complexities, which we'll talk about later. Okay, so a balanced binary tree is one in which the height difference between the left and the right subtree is at most 1. So either all the leaf nodes of the left subtree and the right subtree are at the same level, or one of the left or the right subtree has leaf nodes at a level, let's say, before the level of the other one. That means the difference of the levels should be 1. So let's see an example here. This numbers that I've written next to the nodes, this is the height of the uh, tree, in the sense, when we talk of depth or level, this is level 0, level 1, and level 2. You also have a level 3 here. Okay, so this 3 here is not the level, it is the height. So how do you uh, what is the height of the left subtree? What is the longest path from the root to the leaf? In this case, the longest path is this 1, 2, and 3. So the maximum height that you will be, it will be actually, from level 0 you can go to level 3. So I have actually marked that 3 here to see this is the height. So what is the height of the left subtree? If you just take this part, this is 1 and 2, maximum height. Here the height is 1, or the depth is 1, but I'm looking at the longest path that I can get from the node to the leaf. So in this case, it is 1. So if you calculate the difference between the left subtree and the right subtree, the difference is 1. Here, if you calculate left and right, it's 1 minus 0 or 0 minus 1 without the sign, so it is 1. Now you look here, the left subtree it's similar to the one before. The height is 2 and here it is 0. So 2 minus 0, it is 2, it is not balanced. So for balance, the difference in the heights should be at most 1. Okay, and when that happens, when we talk of balanced trees, when we add or delete an element, if it creates an imbalance in the tree, what we do is we readjust the tree so that all the nodes, they get a height difference of only 1. So just like in case of arrays, when you had to insert, you would push all elements right or left based on whether you're doing insertion or deletion. This is also extra work, but we are only dealing with pointers, and like I said, we have the flexibility to move the entire subtrees right or left or anywhere. So this height adjustment will only be a couple of pointer changes and our tree will be balanced. Now before we move ahead, I want you to go through this picture with full concentration. We are talking of binary trees. So the one that picture that you see in front of you, this is a complete binary tree, or you can say it's a perfect binary tree because right now all the leaf nodes are at the same level. It is complete as well as perfect. Now on the left you see the height of the tree, on the right you see the number of nodes at each level. If the height is 0, the number of nodes is 1. If the height is 1, the number of nodes is 2. If the height is 2, number of nodes is 4. Height is 3, number of nodes is 8. Because it's a binary tree, every node can have 2 children. So if you have 2 nodes, it will have 2 to the power 2, that is 4 children. So this is how we write it. So if you see this 2 here is the, just underline this 2 here is the height of the tree. So if the height of the tree is 2, the number of nodes at that level are 2 to the power 2, which is 4. So if the height is 3, considering you're starting your height from 0. So if the height is 3, the number of nodes at this level is 2 to the power 3. So if the height is h, for example, if I ask you what are the number of nodes at level h of a binary tree, we assume what is the maximum number of nodes that can be there. Okay, so you say it's 2 to the power h. Now let's say this tree grows all the way till height h. What is the total number of nodes in the tree? So we have this number for every level. We'll just add them up, and the sum of all these here gives us the number of nodes in the entire tree. So just add it up. This is a geometric progression with a as 1 and r as 2. And what are the number of terms? The number of terms, you start with 2 to the power 0 and you end with 2 to the power h. So you have h plus 1 terms. So a r is to power the number of terms n minus 1 by r minus 1. So 2 to the power h plus 1 minus 1. Okay. So if the height is, let's say, 3, you have 2 to the power 3 plus 1, which is 4, which is 16 minus 1, you have 15 nodes. Okay. What is the number of leaf nodes? If you're talking, this is 8, 12, 10, sorry, 8 plus 4, 12, 12 plus 2, 14, and plus 1, 15. What is the number of nodes, leaf nodes? If the tree is of height 3, the number of leaf nodes is 8. So what is the height of the tree? If it's 3, the number of leaf nodes will be 2 to the power h. Okay. And if you do 2 into 2 to the power h, which is 2 to the power h plus 1, or 2 into number of leaf nodes minus 1, you get the number of nodes in the tree. And how many internal nodes do you have? including the root, you have 7 internal nodes. And how do you get that? If what is your n? N is the uh, number of nodes in the tree, which is 15. 15 by 2 is 7.5, and floor of that is 7. So you have 7 internal nodes, and you have 8 leaf nodes in the tree. So this is useful at many places, and you'll see we'll be when we uh, move on to your next course, which is algorithms, you'll see this kind of tree structure and this binary tree, number of nodes at each level, and total number of nodes in the tree being used very extensively when we talk of many different types of algorithms, especially sorting algorithms. Okay. Now, if you remember, I had told you in stacks that we have something known as expression trees. You'll see more of expression trees once you go and study your compiler design and parsing, etc. So, what is an expression tree? You have an expression, you want to represent it in the form of a tree. In case of an expression tree, all the internal nodes, all the internal nodes are your operators. Here, if you see in this expression, all the internal nodes are operators, and all the leaf nodes here, they are your operands. Okay. So the application of stack was that you can use stacks to create these expression trees. Okay. Now, let's say for now you have an expression tree created for you. If we traverse the tree, so what do I mean by traversing the tree? When I asked you to do linked list and I asked you to print the linked list, you start from the start pointer, do next, next, and print till you reach the end of the linked list. When we do printing for stack, we do it from bottom to top. Or if we want to print the queue or a doubly linked list in forward direction or reverse direction, we just print the element and move to the next node. Now, how do you print a tree? A tree has a root and it has a left and a right subtree. So when you print a tree, for example, let's go to a simple tree here. Let's go to the original example. So if you want to print this tree, if you print A, what would you print next? Maybe you want to print level by level. So A, B, C, G, D, E, F, H, I. Okay. So when you print A, should you print the leftmost child node B first, or C first, or G first? So you can print in any way you want, but if I am somebody who's interpreting your tree, I print out your tree, so I don't know what order you are following. So what we do in trees, we have some predefined orders in which you can print the tree. So if you tell somebody I have printed the tree in this order, then he'll know what the tree actually looks like. So let's go down to our traversals. So you have already done your uh, conversions from infix to postfix to prefix. So let's get back to this in a while. So let's first finish tree traversal. So when you have a tree, we're dealing with binary tree, so you'll have a left subtree, you'll have a right subtree, and you'll have a root. So you have three. You can start from root, then go to left or right, or you can start from root, go to right, and then left. And we'll follow the same order recursively. We'll see what that means in a while. So basically, if you have left subtree center or the root, and the right subtree, R is the right subtree and 0 is the root, or O is the root. When you have these three, there are 8 combinations that are possible, and out of these, 3 have been chosen as standard. The first one is if you print the left subtree, then the root, and then the right subtree. The order, this order is known as in order. So left, center, right. This is in order. If you prefer to print the center first, and then the left subtree and the right subtree, it is known as pre-order. And if you print the left subtree, the right subtree, and then the root, it is known as post-order. Why I have written in order is infix or pre-order is prefix and post-order is postfix? That's because if you come here to a simple example, if I want to print this tree in order, okay, let's just erase this. If I want to print this tree in order, I'll first print the left subtree. What does the left subtree consist of? A. So I have printed A. Then I'll print the root. So I have printed plus. Then I print the right subtree. Okay. Now right subtree is an expression in itself. So I'll apply the same rule to the right subtree. So I'll print B, then the center, which is multiplication, and then C. So when I follow this rule, I get the infix expression. If I follow the in order rule, which is left, center, right, I get the infix expression. Now, if you want to do pre-order, pre-order means you first print the root. So let me try to draw it here. This is plus sign. So this is root. Then you have the left subtree, which is A. Okay. Then you have the right subtree. So again, right subtree, the order that you follow recursively, it should be pre-order. So pre-order would be, this is multiplication, then B, and then C. So this becomes your prefix expression. Okay. And if you want to do post order means postfix expression. So basically, left subtree, then right subtree. Again, right subtree is a subtree. Again, we apply the same rule. Left, then right. What is the center? Multiplication sign. I just put a star for that. And then this root. So this becomes your postfix expression. If you do the same here and apply it recursively, you will see that Inorder Traversal will give you infix, pre-order will give you prefix, and post-order will give you postfix. Okay, so this is your tree traversals. So whenever you write a program to print, to do anything with the tree, and you want to see what is in the tree, you want to follow an order of the traversal, pre-order, in order, post-order. Now this is an example of a tree which I want to traverse. Actually, this is an example on paper. This is not a coding example. How we code this and how we print something in order or pre-order or post-order, we'll do that later. But for now, if you're given a tree like this, you want to print it in order, for example. So what does in order mean? You take the left subtree first, then you take the root, M, which is here, and then you take the right subtree, which is RT. I have just written RT so that it is understood as left subtree and right subtree. What is your left subtree? Your left subtree has three nodes which you want to print in order. So in order would be P, N, Q, which you have here. Then root is as it is, and then you have the right subtree. Now right subtree has R, O, and it has another subtree. The right side is not just a node, it is a subtree. So I write ST for that. Okay. So we have not yet finished our traversal. So P and Q is your left subtree, M is your center, and R, O. Now ST is left. There is no left here. So empty, which I've shown as a cross, then S, and then V. So V is the right subtree of S. There is no left subtree, so I've shown it as a small cross here. So this is your in order traversal. Now you want to do the same for pre-order. Pre-order means M first, then LT, then RT. Okay. So M, LT, and RT. Now what is LT? LT is again N first and then PQ. So N, PQ. What is right subtree? O and then R and then ST. O, R, and ST. And ST itself is a subtree. So first the root, then the left subtree which is empty, and then the right subtree. So the same goes for postfix, left, right, and center. Left subtree again follow the same root, PQN, which is left, right, and center. Then R, S, and O, not S, actually ST. R, S, T, O, and M is at its place. ST is left, left is empty, right is V, and S is the center. So we are done with the post order traverse. Now if you want to do the same on a expression tree, so understand an expression tree is a tree whose internal nodes are the operators and leaf nodes are the operands. So if I do an in-order traversal of this tree, this is my left subtree, this is my center, this is my right subtree. My left subtree has A, plus is at as it is. What is my right subtree? It is this subtree PT, this star and this F. PT, star and F. And what is PT? PT is B minus C in order. Okay, then into F. Why I've put brackets here? Because when we are actually evaluating an expression tree inside, we are actually taking B and C, applying the operation minus on them, and returning the result. And that result is then multiplied with F. Okay, then similarly, you have the pre-order traversal. You'll see, you'll get the prefix expression, and post-order, you'll get the postfix expression. I've done it in steps. What you can do is you can take the expression, this, convert it into prefix and postfix, and then see whether the tree traversal, when you traverse the tree, whether you get the same thing or not. Okay. Now, this was one last application that was left for uh, stacks. Okay, I want to finish with that. If you have, if you remember, when we had a postfix expression, we could evaluate the expression and get back the infix expression. Or if you had a postfix expression in the form of numbers, you could use stacks to evaluate and get the answer. So what would you get? You would keep on pushing into the stack, and whenever you faced an operator, you would pop out the last two elements, apply the operator, and push back the answer. And when you do it continuously till the end of your postfix expression, you would land up with one element in the stack at the end, which would be your answer. In case of an expression, it would be the infix expression. In case of a uh, numerical example, it would be just one answer, which would be the answer for that postfix expression. Okay. Now, if you want to do the same, we want to create a expression tree using stacks. We follow the same procedure. So you have A, B, and C pushed in. Then you get minus, and then you pop out the last two and apply minus to it. Okay. So pop out B and C, apply B minus C. But now we are not actually applying because we want to construct the expression tree. We are actually creating this part of, or the portion of the tree, B minus C. I have named it RT and I have pushed it back here. And then I push the next element, which is F. So F goes here. F is followed by a multiplication. So I pop out a last two, which is RT and F, create a subtree, and then push it back. I call it ST and I push it back. Then I encounter a plus. Okay, I pop out A and ST, apply this plus here. Okay, and call it FT and push it back here. Okay, now what is this FT? FT is actually A plus ST. What is ST? ST is RT star F. And what is RT? RT is B minus C. So you end up with the final expression. So this is the, what is left in the stack is the, you don't actually store the tree in the stack. You're actually just storing the final, basically pointer to your stack here. Okay, so when we are pushing A and B, we're actually pushing the node addresses. So we're just dealing with addresses here. Okay, so this is your introduction to trees. So what you need to know, what are the trees? This is just a basic introduction without any implementation part. If you have a tree, how do you traverse it? We'll not say we are printing it. How do you traverse a tree? You can do in order, pre-order, post-order traversals. And what are the basics of a binary tree? You should be very well versed with this. What are the different terms that we use? Height, leaf, internal, external, terminal, nodes, and so on. And what kind of binary trees are there? You'll see we'll be going through a few as we proceed with trees. So what we are doing, we are going to do both static and dynamic implementation of trees, and then we'll see how do we add and delete to a tree. And the type of tree that we will deal with is binary search tree. Okay, we'll see what are the properties of binary search tree. So for now, this is your introductory class to trees. Just go through this once, and then we'll go on to our binary search trees. Okay, and that is it. I'll upload the materials and you can go through it, and also through the video once you're done. Thank you.